Students, so we've been doing these abstract theorems and proofs, or we've been reading abstract theorems and doing the abstract proofs. Here's something that's also going to be somewhat abstract, and you might not realize how abstract it is when you first look at it, but any subspace W of a finite dimensional subspace V is also finite dimensional. Okay, and we want to prove this, so we're going to let V be a finite dimensional subspace. And we will prove, and we want to show, W is 2. Okay, well, what's W? Well, what's V? V is finite dimensional, so V must be the span of finitely many vectors, right? That's the definition of being finite dimensional. Okay, so I know that. I know that V is finite dimensional, and I know V is the span of finitely many vectors. I know nothing about W, nothing at all. W, I don't know what the vectors are in W. I can't assume that I can write W as a span. I mean, I can write W as a span. I know that's going to happen, but I don't know how. I don't have it written as a span, and I have to figure out a way to write W as a span if I'm going to write it that way. I'm not given, like, if I was given V is the span of V1 through Vn, and W is the span of W1 through Wm, I know that m is less than n, so I know we have finite dimensional W. Does that make sense? Like, if I'm given that W is a collection of finitely many vectors, I'd know it was finite dimensional because it's the span of finitely many vectors. And not only that, I'd have some bound on the number of vectors that are necessary in order to write it. But I don't have anything like that. So I have to figure this out. So first of all, I'm just going to rule out the trivial case, right? If W is just the zero vector, we're done, because then it's just the span of no vectors, which is just considered to be the zero vector inside V. Okay. Otherwise, we can, what can we do? Well, we can pick some vector in W. Okay, so we can pick some vector in W. And I'm going to call it W1. Okay, so then what do I know? What do I know? Well, if W equals the span of, I want to round, there we go, W1, we are done. So what we're going to do, if not, I'm going to pick some vector in W that's not in the span of W1. And then we're going to repeat. In general, if W is equal to the span of W1, W2 through Wm, we are done. Otherwise, we keep picking. We pick Wm plus 1 in W, which is not in the span of W1. through Wm. Okay, so what we do is we keep picking vectors. So we pick vectors in W, we add it to the span. We know that all of these are vectors in W, so this is contained inside W. Okay, so let's think about this process. There are two possibilities. Either it goes on forever, and we can keep picking vectors. And if it goes on forever, I have a problem. As a matter of fact, it can't even come close to going on forever because it can't ever reach n plus 1. We know that there are only n vectors in V, and we've shown that the number of vectors, if it's higher than n, it must be linearly dependent. And we are picking vectors that are not in the span and forcing ourselves to create a linearly independent set by doing so. So, either it stops or it goes past n. But if this process does not stop, we reach a contradiction when we get to W n plus 1. So the process must stop, and that means, well, at each time we're checking to see if we're done, that means that one of these checks to see that we were done, and there was nothing else that we needed to add. Okay, so this is a really nice thing. Without knowing anything about W at all, I knew that V was the span of finitely many vectors, but without knowing anything about W at all, I started picking vectors inside W. One at a time, I pick each vector inside W. If W is the span of those vectors, I stop and finite dimensional. If not, what I do is I pick a vector in W that is not in the span so far, so it will also be linearly independent because we can't write it as a multiple of the ones before it. We can't write the new vector as a multiple of the ones before it. And by doing this, this process has to end. It can't go on forever. So that's the last abstract result from this section that we needed to cover. So subspaces of finite dimensional vector spaces are also finite dimensional.